In logic, a logical connective is a symbol or word used to connect two or more sentences in a grammatically valid way, such that the sense of the compound sentence produced depends only on the original sentences. The most common logical connectives are binary connectives which join two sentences which can be thought of as the function's operands. Also commonly, negation is considered to be a unary connective. Logical connectives along with quantifiers are the two main types of logical constants used in formal systems such as propositional logic and predicate logic. Semantics of a logical connective is often, but not always, presented as a truth function. A logical connective is similar to but not equivalent to a conditional operator. In language, natural language, in the grammar of natural languages, two sentences may be joined by a grammatical conjunction to form a grammatically compound sentence. Some but not all such grammatical conjunctions are truth functions. For example, consider the following sentences. A. Jack went up the hill. B. Jill went up the hill. C. Jack went up the hill and Jill went up the hill. D. Jack went up the hill so Jill went up the hill. The words an and so are grammatical conjunctions joining the sentences and to form the compound sentences, and the an is a logical connective, since the truth of is completely determined by an. It would make no sense to affirm an but an I. However, so an is not a logical connective, since it would be quite reasonable to affirm an but an I. Perhaps, after all, Jill went up the hill to fetch a pail of water, not because Jack had gone up the hill at all. Various English words and word pairs express logical connectives, and some of them are synonymous. Examples are and then within, or either, or implies, if then, if and only if, just in case, but, however, not both, neither, nor. The word not and the phrases it is false that and it is not the case that also express a logical connective, even though they are applied to a single statement. In do not connect two statements. Formal languages. In formal languages, truth functions are represented by unambiguous symbols. These symbols are called logical connectives, logical operators, propositional operators, or, in classical logic, truth functional connectives. See well-formed formula for the rules which allow new well-formed formulas to be constructed by joining other well-formed formulas using truth functional connectives. Logical connectives can be used to link more than two statements, so one can speak about nary logical connective. Common logical connectives. List of common logical connectives. Commonly used logical connectives include negation, n, conjunction, k, and disjunction, a, material implication, c, biconditional, e. Alternative names for biconditional are iff, xnor, and by implication. For example, the meaning of the statements "it is raining" and "I am indoors" is transformed when the two are combined with logical connectives. For statement P equals "it is raining" and Q equals "I am indoors," it is not raining. It is raining and I am indoors. It is raining or I am indoors. If it is raining, then I am indoors. If I am indoors, then it is raining. I am indoors if and only if it is raining. It is also common to consider the always true formula and the always false formula to be connective. True formula, false formula. History of notations. Negation. The symbol appeared in Hating in 1929. The symbol tilde appeared in Russell in 1908. An alternative notation is to add an horizontal line on top of the formula, as in. Another alternative notation is to use a prime symbol as in P. Conjunction. The symbol appeared in Hating in 1929, and appeared at least in Schonfinkel in 1924. Comes from Boole's interpretation of logic as an elementary algebra. Disjunction. The symbol appeared in Russell in 1908. The symbol plus is also used, in spite of the ambiguity coming from the fact that the plus of ordinary elementary algebra is an exclusive or when interpreted logically in a two-element ring. Punctually in the history, a plus together with a dot in the lower right corner has been used by Piesk. Implication. The symbol can be seen in Hilbert in 1917, was used by Russell in 1908, was used in Vax. Biconditional. The symbol was used at least by Russell in 1908, was used at least by Tashi in 1940, was used in Vax. Other symbols appeared punctually in the history, such as in Gentzen, tilde in Schonfinkel or in Chazal. True. The symbol 1 comes from Boole's interpretation of logic as an elementary algebra over the two-element Boolean algebra. Other notations include to be found in Pino. False. The symbol 0 comes also from Boole's interpretation of logic as a ring. Other notations include to be found in Pino. Some authors used letters for connectives at some time of the history. U for conjunction and O for disjunction in earlier works by Hilbert, NP for negation, KPQ for conjunction, DPQ for alternative denial, APQ for disjunction, XPQ for joint denial, CPQ for implication, EPQ for biconditional in Lukasiewicz, cf. Polish notation. Redundancy. Such a logical connective as converse implication is actually the same as material conditional with swapped arguments. Thus, the symbol for converse implication is redundant. In some logical calculi, certain essentially different compound statements are logically equivalent. A less trivial example of a redundancy is the classical equivalence between PQ and PQ. Therefore, a classical-based logical system does not need the conditional operator if and are already in use, or may use the only as a syntactic sugar for a compound having one negation and one disjunction. There are 16 Boolean functions associating the input truth values P and Q with 4-digit binary outputs. These correspond to possible choices of binary logical connectives for classical logic. Different implementations of classical logic can choose different functionally complete subsets of connectives. One approach is to choose a minimal set, and define other connectives by some logical form, as in the example with the material conditional above. The following are the minimal functionally complete sets of operators in classical logic whose arities do not exceed 2. 1 element, 2 elements, 3 elements. See more details about functional completeness in classical logic at functional completeness in truth function. Another approach is to use with equal rights connectives of a certain convenient in functionally complete, but not minimal set. This approach requires more propositional axioms, and each equivalence between logical forms must be either an axiom or provable as a theorem. The situation, however, is more complicated in intuitionistic logic. Of its 5 connectives, only negation can be reduced to other connectives. Neither conjunction, disjunction, nor material conditional has an equivalent form constructed of the other 4 logical connectives. Properties. Some logical connectives possess properties which may be expressed in the theorems containing the connective. Some of those properties that a logical connective may have are associativity. Within an expression containing 2 or more of the same associative connectives in a row, the order of the operations does not matter as long as the sequence of the operands is not changed. Commutativity. The operands of the connective may be swapped, preserving logical equivalence to the original expression. Distributivity. A connective denoted by distributes over another connective denoted by plus, if A equals plus for all operands A, B, C. Idempotence. Whenever the operands of the operation are the same, the compound is logically equivalent to the operand. Absorption. A pair of connectives satisfies the absorption law if for all operands A, B. Monotonicity. If FF for all A1 and B1, Bn 0, 1, such that A1 B1, A2 B2, and Bn, e.g. Affinity. Each variable always makes a difference in the truth value of the operation, or it never makes a difference. E.g., duality. To read the truth value assignments for the operation from top to bottom on its truth table is the same as taking the complement of reading the table of the same or another connective from bottom to top. Without resorting to truth tables, it may be formulated as G equals G. E.g., truth preserving. The compound all those argument to tautologies is a tautology itself. E.g., falsehood preserving. The compound all those argument to contradictions is a contradiction itself. E.g., involutivity. F equals A. E.g., negation in classical logic. For classical and intuitionistic logic, the equals symbol means that corresponding implications, and for logical compounds can be both proved as theorems, and the symbol means that for logical compounds is a consequence of corresponding connectives for propositional variables. Some many-valued logics may have incompatible definitions of equivalence and order. Both conjunction and disjunction are associative, commutative and idempotent in classical logic. Most varieties of many-valued logic and intuitionistic logic. The same is true about distributivity of conjunction over disjunction and disjunction over conjunction, as well as for the absorption law. In classical logic and some varieties of many-valued logic, conjunction and disjunction are dual, and negation is self-dual. The latter is also self-dual in intuitionistic logic. Order of precedence. As a way of reducing the number of necessary parentheses, one may introduce precedence rules. Has higher precedence than, higher than, and higher than. So for example, is short for. Here is a table that shows a commonly used precedence of logical operators. However, not all authors use the same order. For instance, an ordering in which disjunction is lower precedence than implication or by implication has also been used. Sometimes precedence between conjunction and disjunction is unspecified, requiring to provide it explicitly in given formula with parentheses. The order of precedence determines which connective is the main connective when interpreting a non-atomic formula. Computer science. A truth-functional approach to logical operators is implemented as logic gates in digital circuits. Practically all digital circuits are built up from NAND, NOR, NOT, and transmission gates. See more details in truth function in computer science. Logical operators over bit vectors are bitwise operations. But not every usage of a logical connective in computer programming has a Boolean semantic. For example, lazy evaluation is sometimes implemented for PQ and PQ, so these connectives are not commutative if some of expressions P, Q has side effects. Also, a conditional, which in some sense corresponds to the material conditional connective, is essentially non-Boolean because for if then Q, the consequent Q is not executed if the antecedent P is false. This is closer to intuitionist and constructivist views on the material conditional, rather than to classical logic's ones.